I believe that you guys asked me to review voltage division, current division, superposition, and Thevenin and Norton equivalent circuits when we wrap things up last Wednesday. So let's do just that before we get into the lab. So let's say that I have a voltage source that is 20 angle 0 degrees volts connected to some impedance ZA that I will define shortly. Here we have an impedance ZB. Put a current source here that is 2 angle 10 degrees amps. Call this ZC. This ZD. And this voltage source will be 12 angle 45 degrees volts over here. And our ultimate goal in this problem is to determine the phasor voltage drop over impedance ZC, which I've labeled as VC. Okay. And we are going to do this using superposition. So let's start with, if I call this guy over here VS1 on, this guy over here, just to be clear, VS2 off and IS off. So with only our left voltage source on, we're going to have something that looks like this. We'll have our 20 angle 0 degrees volt source on. Oh, sorry. I need to give us numbers for ZA, B, C, and D as well. So let's just call this 8 plus J2, 5 minus J1, 10 angle 70 degrees, and 4 angle negative 50 degrees. Having numbers to use generally helps. So back to our redrawing with that voltage source on. Since our current source is going to look like an open circuit, I'm just not going to draw it at all since it's effectively removed. So here is ZC. And since our 12 angle 45 degree source is a short circuit, I'm just going to slide ZD down over here to the right, like so. And we are trying to determine this phasor voltage, VC prime. Okay. So there are a couple of different ways that we could do this, but I'm going to specifically do it using voltage division because you guys asked for me to review voltage division. Okay. So what I'm going to do first is I'm going to call this voltage VB prime, okay? And I'm going to talk you through what I'm going to do because I'm going to do it in a single step, all right? So how many of you feel like we could figure out what that voltage VB prime is using voltage division? Yeah, so VB prime would just be the voltage drop over impedance ZB in parallel with the series combination of ZC and ZD. Well, VC prime can be determined by applying voltage division once we know what VB prime is, right? So I am saying that VC prime is going to be VB prime, where VB prime would be 20 angle 0 degrees volts multiplied by, let me give myself enough room here, ZB times ZC plus ZD over ZB plus ZC plus ZD. And then in our denominator, we're going to have ZA plus that same thing. So that's one application of voltage division to give us VB prime. And now we'll do our second application of voltage division. So we're going to multiply effectively VB prime times VC over VC plus ZD, like so. So we're applying voltage division twice here to get our result in a single expression, because I feel roughly 2 months and change in to applying voltage division that we should be able to make sense of this. Okay. So let's take a moment, or actually several moments, given how complex this is, to evaluate our numerical result here. How I would approach something like this would be to store all of those impedances A, B, C, and D in my calculator as literally A, B, C, and D, so that I don't have to do all that much bookkeeping and typing that kind of stuff in, and then allow the calculator to do the majority of the heavy lifting. So I'm going to have 8 plus 2I, store that as A. 5 minus 1I, store that as B. 10 angle 70, stored as C. And 4 angle negative 50, stored as D. And so I'm going to have 20 times B times C plus D over B plus C plus D over A plus B times C plus D over B plus C plus D. All of this multiplied by C over C plus D. So for those of you who have Casio calculators, particularly the FX 115, putting this much math in might cause it to freak out. So what you would have to do is break it into digestible bits here. So effectively make each fraction its own quantity and then just multiply them out. So I get 7.029 with an angle of 20.193 degrees volts. All right. So how did we feel about this level of analysis? Or I guess it really wasn't a whole heck of a lot of analysis at all. I saw this as a voltage source connected to impedances in series. And so I just used voltage division to get VB. And then again, a second application of voltage division, because once I know the voltage drop over impedance B in parallel with the series combination of C and D, I can then use voltage division one more time to get the voltage drop over just impedance C by itself. All right, so you're either all on board or all utterly confused. It's one or the other since nobody's saying anything. I'm going to assume you're on board. Let's talk about with our voltage sources off and our current source on. So VS1 and VS2 off, IS. So with VS1 off, we replace it with a short circuit. Here's ZA. ZB. Here's our current source, which was 2 angle 10. Here's ZC. And over here is ZD. And again, we were looking for this quantity VC, and I'm going to call it VC double prime since this is our second iteration of superposition. And what I am going to do is I'm going to use current division and Ohm's law in order to determine what that quantity is. Okay. So if I'm employing current division, what I'm trying to figure out is this current, which I'm going to call ICD, because that current is flowing through the series combination of impedance ZC and impedance ZD. Using Ohm's law, then, the voltage drop VC double prime will just be ICD multiplied by ZC. So from this, we'll have VC double prime is equal to 2 angle 10 degrees amps times 1 over ZC plus ZD divided by 1 over ZA plus 1 over ZB plus 1 over ZC plus ZD. And then all of this multiplied by ZC. Again, doing it all in one step because I feel at this point we should be comfortable with that level of theory application. And I'm just going to throw this into my calculator using my previously stored variables for the impedances. I get 5.796 angle 44.229 degrees volts. So to be clear, what I have done here is I have applied current division, which is this part. Figure out how much current branches off from that 2 angle 10 degree source and flows to the right through the branch that contains the impedance ZC and ZD in series, which is why in my numerator I have 1 over ZC plus ZD. And because we're applying current division, our denominator should then be 1 over the impedance of each of those branches. All right, so for our third application of superposition, we will have VS1 and IS off and VS2 on. So that means we're going to have a short circuit here. Here's ZA, ZB, C, ZD, and then our voltage source VS2, whose numerical value I can't remember, 12 angle 45. And we are trying to find VC triple prime now. So I'm going to do voltage division again. I'm going to be able to get it all in one voltage division relationship this time. So we could say that VC triple prime in this case is going to be 12 angle 45 degrees volts times VC over ZD plus ZC plus ZA/ZB over ZA plus ZB, because we see those two impedances on the left as in parallel. Now, I have intentionally made a mistake here. What is it? I'm not including something that needs to be in there.
Is it the sinusoidal?
A negative sign. Absolutely right. There should be a negative sign right here, right? Because when we're applying voltage division, we would expect this polarity. So this would be VD triple prime. This would be VB triple prime. And we would expect to see DC triple prime like so, where the sum of the drops is equal to the source voltage, but we have an opposite polarity here, which means we need to include that negative sign in order to get the correct answer. So if I put this in, negative 12 angle 45 times C over D plus C plus A times B over A plus B. I get 10.784 with an angle of negative 99.099 degrees volts. And since I want to do this all on one page, we could say then that VC is VC prime plus VC double prime plus VC triple prime. And I conveniently stored the results of my three superpositions as variables in my calculator. That's one of the things I love about the TIs is you can store up to 8 variables. So for me, this is going to look like X plus Y plus Z, or 9.963 with an angle of negative 24.798 degrees. So in solving the problem that particular way, we reviewed superposition and the rules that are associated with that. So anytime we have, we want to turn off a voltage source, we replace it with a short circuit. Anytime we want to turn off a current source, we replace it with an open circuit. We also revisited the rules regarding voltage division and current division. So what we are going to do now is work this problem again using the concept of Thevenin and Norton equivalent circuits to verify that we get the same result. So I'm just going to scroll up here real quick and effectively just make a copy of this bit here. And then I'm go to my next page. Like so. All right. So what we are going to do, let me see what's going on in chat. What was the reason for having a negative sign for the voltage division? Let me go back to that real quick, Michael, and I will explain it again. So whenever we established the rules for voltage division, we did so where the positive polarity of the voltage drop was effectively touching the positive polarity of the source voltage. And so what I mean by that is I'm talking about we have a positive sign here and a positive sign here. so that the sum of the voltage drops, in this case, VD plus VC plus VB, is equal to our source voltage, okay? So all of the polarities are assumed, in this case, to be, kind of positive polarity on the right or positive polarity on top as we follow the current around the loop. So another way to think about this, let me do this in pink here, is that as our current leaves our source, we expect it to be leaving from the positive polarity terminal, and we expect this current flowing into the positive polarity terminal of our impedances in this case. Well, since the current is flowing into the negative polarity terminal of impedance ZC, we need to include that negative sign to correct things. So we can either think about it from the relationship of what the current is doing as it leaves the voltage source, or we can think about it in terms of the polarities of the voltage drops with respect to the voltage source. They both amount to literally the exact same thing. All right. So what we are going to do here is we are going to find the Thevenin equivalent circuit with respect to impedance ZC, and then use the Thevenin equivalent circuit to find the voltage drop over VC at the end, okay? So whenever we're finding the Thevenin equivalent with respect to a particular circuit element, what do? We have to take the element in question out of the circuit, right? So that means that we're going to be looking at this guy. Leaving behind an open circuit set of terminals where impedance ZC used to be connected. Now, because I don't want to wind up getting a system of equations, I am not going to use mesh analysis or anything like that here, okay? And so I'm not going to find the Norton current because that would give me a 3-loop system that would be, would take a lot more work to do than finding the Thevenin equivalent voltage and the Thevenin equivalent impedance, okay? So let's define our Thevenin voltage, VTH, like so. All right. So we are going to determine this quantity by effectively just what our last step is going to be is effectively to apply Kirchhoff's voltage law around this loop and solve for the quantity VTH, at least the way that my brain is interpreting how we should work this. So what that means effectively is that I'm going to have a voltage on the left-hand side of the open circuit, and I'm going to have a voltage on the right-hand side of the open circuit, and the difference of those two voltages is going to be VTH. Does that track here? Okay. Well, let's talk very briefly about what the voltage is going to be on the right-hand side of the circuit. Anybody have any thoughts? Pardon? So the voltage drop across ZD will have something to do with it, but what is the voltage drop across ZD? We should be able to see by inspection what that value is. It's 0. And the reason why the voltage drop across impedance ZD is 0 is because ZD isn't part of a closed current carrying loop. So the voltage drop on the right-hand side, or the voltage drop associated with the negative polarity terminal of our Thevenin voltage, is just 12 angle 45. So we don't even have to really do any work for that whatsoever, as long as we can acknowledge and remember that voltage drops don't occur over elements that aren't connected to anything. Okay. So that begs the question then, how do we find the voltage drop associated with the left-hand side of the circuit? And there are a couple of different ways that we could do this, okay? We could apply Kirchhoff's current law to the left-hand side of the circuit effectively, and then solve for that unknown nodal voltage. And I talked to some of you guys about doing things like that at the end of class on Wednesday. Instead, just for the sake of argument, you didn't ask for it, but I'm going to enforce you. Let's do a source transformation here, okay? So if we did a source transformation, what we would have is a current source whose value is simply 20 angle 0 divided by ZA in parallel with ZA, connected then in parallel to ZB, and finally in parallel to the current 2 angle 10 degrees amps. From here, we can easily use Ohm's law to figure out what the voltage is that's associated with the positive polarity terminal. And from this, we can say that our Thevenin voltage, VTH, is 20 angle 0 degrees volts divided by ZA plus 2 angle 10 degrees amps. I'm just combining those two parallel current sources into a single equivalent current source. And then I'm going to multiply it by the impedance that's in parallel with that equivalent voltage, current source, which is simply ZA times ZB over ZA plus ZB. And then lastly, I'm going to remember to subtract that 12 angle 45 degrees volts. So this is what my Thevenin voltage would look like in one go. So I'm going to throw this into my calculator. So that's 20 over A plus 2 angle 10 times A times B over A plus B minus 12 angle 45. And I get a Thevenin voltage of 11.087 angle negative 60.700 degrees. So that's my Thevenin voltage. How am I going to get my Thevenin impedance? With my Thevenin impedance, I just need to be looking at a dead network, right? So let's look at this representation right here, where we've turned off all of our independent sources. What do we see? To me, I see ZD in series with the parallel combination of ZA and ZB. So ZTH is ZD plus ZA times ZB over ZA plus ZB. So that's going to be, let's see, D plus A times B over A plus B. Which I get to be 6.599. Angle of negative 28.592 degrees ohms. And from here, we can replace all of that messiness with the following circuit. So here we have our Thevenin voltage. Here we have our Thevenin impedance. Here we have ZC. And our goal is to determine what the voltage drop over VC is. Using voltage division, VC is simply VTH times ZC over ZC plus ZTH. And wouldn't you know it, I saved VTH and ZTH in my calculator because I knew what I was going to do here. And so to me, that's going to look like X times C over C plus Y and I get 9.963 with an angle of negative 24.798 degrees volts. And I'm just going to scroll up here. And what do you know? I got the exact same result. So two different ways, two vastly different ways to work this problem, right? That both yielded the exact same result, which to me means we applied the different methods correctly. So we have reviewed superposition. We have reviewed voltage division, current division, Thevenin equivalent circuits, source transformations, Ohm's law, anything else that we need to prove works in the frequency domain. As I stated before, the whole point of analyzing circuits in the frequency domain is that we can use our DC-based relationships, or our DC circuit analysis techniques, using complex numbers to make our relationships look like algebra in the frequency domain when they would be calculus and trig-based in the time domain. So frequency domain techniques are obviously a much more succinct way to analyze these circuits. Yes, sir.
The source transformation that we did, couldn't we have done the other way, like transform the.
All right, so let's look at that really quick. Because when I was thinking about what I was going to talk about this morning, that was where my mind first went, but it won't work out as prettily. So let me explain exactly why. Okay. So I'm going to put ZA back here. Question is, what if we did the source transformation on the practical current source as opposed to the practical voltage source, right? Well, what's going to happen is that we're going to wind up with a voltage source that is 2 angle 10 degrees amps times ZB in series with ZB, which actually just makes this look more gross. And sorry, this should have been a voltage source here. And so the reason why it comes out this way is because ZB and the current source are between this node. That's not what I wanted to have happen. And this node down here. So when we disconnect that practical current source, we have to put it back between those two same nodes, which makes it a little wonky. Now, I say that that's ugly, but we could treat the left-hand side there as a single loop circuit and figure out what that voltage drop is in 1 to 2 steps. But that's still a few more steps than doing the practical source transformation with the practical voltage source on the left. So you could absolutely get there doing it that way, but I would argue that converting the voltage source into a current source is a more efficient path. Yeah. No, when I first eyeballed it, I was like, oh, I'm going to have voltage sources in series and everything's going to be great. But nope. Yes, sir.
So this has nothing to do with that, but on web work, so some of them you have to add to like 360 or 180 to get the degree correct in web work. Will we have to do that on the exam too?
So you're talking with regards to leading and lagging and things like that. So adding, so let me be very, very clear here. Adding or subtracting 180 degrees is the same as multiplying by a factor of -1. That is entirely different than adding or subtracting 360 degrees, because that's effectively multiplying by a factor of +1. Okay. Now, for the leading and lagging problems, specifically, I don't believe that you will need to do that because I write the problems based exactly on the way that I taught that material. But your human brain has the ability to interpret, adding and subtracting 360 maybe a little bit more easily than the computer does, because effectively what the computer is looking for is a number, hard and fast. It has to be this number. But it doesn't realize that that number is an angle and that there are equivalencies between angles that are 360 degrees apart from each other. Whereas we hopefully possess the mathematical skills to understand that. So long story short, I do not anticipate you having to do that if you follow the methodology that I outlined in class. Leading being measuring angles in a counterclockwise direction, lagging being measuring angles in a clockwise direction, and you're always going to wind up with a positive number. But there are other ways to think about it that you could have to do that. Does that make sense? Okay. Garrett. So the reason that I try to avoid systems of equations whenever possible with these complex number problems is because our calculators that we are allowed to use for exams and stuff in this class are not capable of solving a system that utilizes complex numbers. And what I mean very specifically by that is that you can't just put that into your equation solver and let it rip. You can absolutely use techniques that you learned in your pre-calculus classes like Kramer's rule and things like that to solve the system of equations that involve complex numbers using your calculator. But it's, let's just say, very tedious to do so. So I try to make sure that for any problem I give you where I'm expecting a numerical solution, there is a way to do it that does not involve setting up a system of equations. That way will usually involve some sort of source transformation or the application of superposition. Now, as we discussed for those of us that were physically here last Wednesday, we can fudge our way through nodal when we only have one voltage quantity of interest to solve for, and then we can use that to get all of our other relationships if needed. So, for example, with this same circuit, what we could do is say that this bottom node is our reference, and this nodal voltage up here is Vx. If we applied Kirchhoff's current law at node X, we would have Vx minus 20 angle 0 degrees volts over ZA plus Vx over ZB minus 2 angle 10 degrees amps plus Vx minus 12 angle 45 degrees. Sorry, I forgot my unit there. Volts divided by ZC plus ZD is equal to 0. Where what I've done there is I've combined impedances ZC and ZD into a single impedance to effectively eliminate that node point that's between those two, giving myself a one equation, one unknown system, as it were, to solve using algebra. After I solve for Vx, I could say that IC, the current flowing through impedance ZC, would simply be Vx minus 12 angle 45 degrees volts over ZC plus ZD, and therefore VC simply IC times ZC. That is a different way to solve it than the ways that we've previously discussed. That does technically involve setting up a system, but it's a one equation, one unknown system that we can just use algebra and not have to rely on our calculator too heavily for that. So that's always potentially in play as well. Okay. There will never be a problem on my exam 3, steady state sinusoidal analysis, that will require you to use nodal or mesh analysis with more than one variable, because making you solve for that just takes too damn long. Did that help answer your question? All right, anything else? All righty, well, my goal for these last couple of class meetings was to illustrate to you all that all of our DC circuit analysis techniques are once again fair game here in the frequency domain. So I don't have an in-class assignment prepared for you guys for today, simply because all we really did was review things. So for the remainder of the class meeting, we do have a lab. I don't think it'll take you the full hour. It may, but I would like for you guys to work on that. And what we're going to do for the remaining few class meetings, I think we have 3 or 4 more class meetings prior to our final, is we are going to start developing power relationships for these steady state sinusoidal circuits. And that'll be 3 days worth of stuff, culminating with a lab, I believe, at the end of class next Monday. And then for those of you who are not graduating seniors, you take your final on Wednesday. For those of you who are graduating seniors, you have to take your final with me on Monday night because your grades are due on Tuesday.